Let us now use Maple to do the averaging calculation that I was discussing on the blackboard in the last lecture. So I'll start like this. I'll say dE is equal to the following: x dot plus epsilon times x times sine of t plus x. That's what I had last time. That's all we had last time, this being equal to 0. But I'm going to add something here. I'm going to add that here, and just to make it a little more interesting, later when I set p equals 0, we will just have what we were doing earlier. Okay, so as discussed in the lecture, I start with a near identity transformation. I will put 3 or something. Let me put n equals 3, nit equals add. What do I have to do now? I have to do x equals x bar plus add epsilon to the power k times sum w of wk of x bar t, k equals 1 to n. Okay, so with luck, if my program works well, I can do third order averaging or second order averaging or anything. I'll do 2 here for the moment. Then later we will try third order averaging also. Okay, this expression has to be substituted into the right hand side, not here. So I come here and I say dEA is equal to substitute NIT in dE. Okay, so it has got substituted here on the right hand side, but not yet here. Now for x dot, I have to differentiate the NIT part. So what I will do is I will say temp is equal to substitute NIT in x. That pulls out the right hand side, and I will say x ds, the thing that I'm going to substitute in place of x dot, is equal to the derivative of temp with respect to x bar times x bar dot plus the derivative of temp with respect to t. This is what x dot is. Okay, that has to go there, which is also the same as going here. And so now I will say dEA again is equal to substitute x dot equals x ds in dEA, and that's this expression here. It's fairly long, but let me do an expansion in epsilon and show you. So I will say Taylor dEA epsilon 3, just to show you something. And you see here is x bar dot, this is order epsilon, this is order epsilon cube, and so on, and this whole thing has to be equal to 0. The only way that works is if x bar dot is order epsilon. Okay, for this reason, this is just for demonstration, so I'm going to remove that again, and I will say xd sub, the substitution, is equal to the following: x bar dot equals add epsilon to the power k times a k, k equals 1 to n. When I do third order, I will have another term here. In this problem, I know that a1 will turn out to be 0. a2 is of interest, but in general now we are discussing a method for doing higher order averaging. Very good. This is going to be substituted in here. Okay, so now we say dEA is equal to substitute xd sub, this equation, in dEA. Okay, this long expression now needs to be Taylor expanded so that we can see how the terms are falling. I'll call that dEB is equal to convert Taylor DEA epsilon n plus 1 polynomial. Okay, and now you see, because we are doing up to second order in this calculation, so here is order epsilon, here is second order. Over here W1 appears only with a time derivative. Over here W1 appears explicitly, W2 appears only with a time derivative. And if we go to another order, then W3 will appear only with a time derivative, and so on. That's the first thing to note. The second thing to note is that this quantity, for it to be 0, this is the part that comes from the differential equation. It in general has a non-oscillating part which could be not 0, that would be absorbed by this, and it has an oscillating part with 0 mean that will be absorbed here. If a non-zero mean was also absorbed here, then this will give you a linearly increasing component and your expansion will break down faster than it needs to. So that is why we will not keep any non-zero mean from here in the del W1 del T. We will put that there and it will give us an expansion that will work for as long as possible. To find this one and this one, it is simple to pull it out, temporarily set this one and this one equal to 0. So that's what we will do now, and I will try to write it in a loop and try my luck. So I'll say for k from 1 to n, do temp is equal to the coefficient in DEB of epsilon to the power k. So I've pulled that out. Okay, I say temp 1 is equal to expand, substitute a k equals 0 and w k of x bar t equals 0 in temp. Okay, so now I've got temp 1. Now this is just this part here for this problem, right? So now I will calculate its average value. In this case I know the average is 0, but in any case I'll calculate it. So I'll say temp 2 is equal to simplify integrate temp 1 t equals 0 to 2 times pi by 2 times pi and that is the average part. Okay, now actually I don't well, it's okay, I found the average part, and then I will say temp 3 is equal to ak equals minus temp 2. Okay, so that's the average part. I found that. In this case a1 will be 0, a2 will be not 0. We'll see how that works out. Okay, so then after I found this, where do I substitute it? So I substitute it in, first of all, in xd sub, because that's my main interest. So I say xd sub equals substitute temp 3 in xd sub. That's my first job done. The next thing I want to do is I want to substitute it not just here but here as well, because the a1 may appear here. Look, it does, right? So it appears at higher order terms. So what I will do now is I will say DEB is equal to substitute temp 3 in DEB. Maybe I can simplify in case that helps, but if I do, then I should do collect for epsilon Okay, so now I've got DEB again. The A1 has removed these things here. Okay, so now let me pull it out again. So once again, temp is equal to the coefficient in DEB of epsilon to the power k. Maybe I will use combined trig. Okay, so I've simplified that. The A1 part has gone. The del W1 del T is still there. What I will do now is I will say temp1 is equal to, or if I do expand, then this combined trig is of no use. So maybe I won't do it here. It's not needed, or it's not helping me. Temp1 is equal to expand, substitute wk of x bar t equals 0 in temp. Okay, so now I've got the zero mean part of that. I integrate and set it equal to this one over here. Integrate with respect to time. So I say temp2 is equal to minus integrate temp1 t, and that's actually what W1 is. Okay, so then I say temp3 is equal to wk of x bar t is equal to temp2, and now my job is done at this order, and I say DEB is equal to expand, substitute temp3 in DEB collect for epsilon. There's something else I want to do, and that is I want to substitute it into NIT. So I say NIT is equal to substitute temp3 in NIT, and I say end. With luck, this will run. It ran and it gave me some kind of long expressions, but let's see. DEB. Okay, there's a quadratic term. Let's try combine that trig. 0. So that part is dead. There's no problem. Okay, combine NIT trig. Okay, so that's what the solution is. When I get x bar, this is what I have to do. I will do substitute the previous into x, and then I will say collect for epsilon. Okay, and then x is equal to x bar times this thing times epsilon times this thing times epsilon square. Okay, and finally, of course, the real main thing that we are interested in is x ds. All the way up, xd sub. Okay, have I substituted into xd sub? Sorry for the long expressions. xd sub I've substituted here, and you see, so this is my final answer. Okay, so that's my answer. That's my answer. And if p is 0, then of course it's particularly easy. That is what we had in MATLAB earlier, and we will see the validity of that now. So here, if p is 0, then this is 2 and that's 4, so minus epsilon square x square by 2. We'll see that in MATLAB here. Epsilon I've taken as 0.05. You will see that it is matching, and when I do open this one, you can see that that is the original equation. Okay, so now I'll come here and I will say OP equals, and then I will do Tx equals ODE45 simp average 0, 500, maybe an initial condition of 3. This is the Wiggly full solution. Okay, so you see that that's what the solution looks like. And then I can come here and I can go to my averaged equation. So I'll do hold on, and then I can do simp av2 with essentially with the same initial condition, and then I'll plot the answer with red, and you can see that the match is good. If you look here, this red line, I hope you can see it, you will see that it's clearly correct. If I use a smaller value like 2 here and 0.02 here, and if I take maybe 1500, now I'm doing the full solution. What happened? This can't be there. Okay, so that's the Wiggly solution. You know, if you look in here, you will see that it has this oscillatory part, and then I can this is the averaged one, also 1500 with red, and you can see there's a red line here. In fact, I can do this as follows. And then you can see the red line more clearly, and it is clear that the averaging works pretty well. If we go back to the Maple equation now, Maple file now, what I will do is I will show you maybe 4th order, just because the program can. Okay, so now the expressions are getting a bit bigger, and so I will suppress display, and I will suppress display. It's taking a while to compute, and then combine. So we hope that it is 0, which it is, and then the expression, of course, here for the solution is very long. That can't be helped. That's the approximate solution. It's very long, but let's just look here, and here is the epsilon squared term, and here is the epsilon cubed term. It's got sine and whatnot, right? There should be an epsilon 4th term. Okay, so there is actually some non-uniqueness in the higher non-trivial orders, but this is the part that we are usually most interested in. Usually the first non-zero average rate of change is the one we are most interested in. So you can see there is this 2 plus p squared term that is coming, and you can verify that with your own numerical simulations if you like. I'll stop here.